Today we are going to do section 1.1, page 7. But before I start, I want you to take a look at this. Here are some problems I got out of the homework section on page 21. Now, if you look at this stuff, being that this is a review section, please look at this and see what you think of it. If you think that, oh, I know this stuff inside out, then you can skip this section and go to the next one, and perhaps skip the entire chapter 1. If you feel like I'm about 90%, 95%, 75%, 30%, then let's go through this section. The goal is that you must know this stuff like inside out, like you can do it in your sleep. Okay, I don't mean this for the entire algebra course. It's just that this review section in entire chapter 1 and part of chapter 2 is extremely important at being able to handle the rest of the algebra. And the only way you can do it is if you know this stuff inside out. So if you don't know this stuff inside out, please work on it. And but if you do, please skip this section. Okay, So for those who plan to not skip, let's continue and go over this review of stuff that was taught in pre-algebra. First, what are real numbers? Real numbers are just every number you can think of, okay? And having said that, let's turn the page. And on page 8, when we consider natural numbers are numbers that you normally count with. It starts at 1 and it goes up to 2, 3, 4, 5, etc. Okay, and then the whole number, well, there's a slight definition where whole number counts 0, 2 as part of natural numbers. That's not particularly interesting. Now, integers include positive integers and negative integers. So they are natural numbers, but you might slap a negative sign on it. And then rational numbers are fractions. Okay, all rational doesn't mean it's rational. It means it comes from ratio. Okay, and ratio is a fraction. And then next we can look at. So a rational number can be a fraction, or it can be some kind of decimal point. And like 1/3 can be represented as 0.333, and it keeps going on forever. So that would be the difference. Irrational numbers are numbers that cannot be represented by a fraction. For example, the square root of 2. Or pi. Those are very standard. Those are irrational, not because they're irrational, but there's no way to represent them with ratios. Okay, and let's turn the page. I am now on page 10. Let's look at page 10, which talks about the number line. The entire set of real numbers. Remember, real number is all those numbers we mentioned. Okay, they have a collective name called real numbers. The real numbers can be represented on a line that's called the number line. The number line it has a 0 in there usually somewhere, whereas over here is the positive side where you go 1, 2, 3. Okay, and then in 3 there's pi right there. Okay, 3.14, etc. And then there's negative numbers, -1, -2, and then there you might have something in here such as negative square root of 2. And so the number line is a visual way of representing all numbers. The number line doesn't stop, okay? Just keep going on both directions forever. And that would be the number line. So that now let's look at page 11, where we talk about the concept of sets. The concept of sets means is just how we talk about things. The biggest set in what we've talked about so far are the real numbers. Okay, so that's the biggest circle, and then within the set of real numbers, we might have the set of irrational numbers, and also the set of rational numbers, which are two distinct groups. And then, but within the set of rational numbers, we have, say, the set of integers, within which we have the set of natural numbers or something? Well, whatever, okay? But anyway, the concept of set just means that we have a name for a group. We have a big group, and then we might have small groups. And the set is sometimes written like this. For example, you might have, say, you might see some kind of notation like this, okay? For example, I have a set which is a 0, 1, 2. That is a set of 3 numbers only. Or I have a set that goes from 2, 3, and then it keeps going forever. So I might denote the set that way. Okay, and then there's another way of denoting set is that draw a line. You say m over n. Draw a vertical line where you describe m and n are integers, where n is not 0. N is not 0 because denominator cannot be 0. It's not possible to divide by 0, so we specify n is not 0. Now this set notation, when I say notation, I'm talking about what is this saying, okay? There's no math in here, just talk. So what this says is my set consists of any fraction m over n, where m and n themselves are integers. One example would be, say, 1/2. Okay, any integer, say minus 1 over 3, or 2 over 50, or minus 3 over 100, something like that. As long as it fits m and integers, then my set is the item belongs to my set. So as you can imagine, my set is extremely big, right? It has, in fact, infinite number of infinite amount of stuff in it. This set is also infinite because my dots means this doesn't end. It just keeps going to 1 billion and doesn't stop there either. Whereas this is a limited set because I only got 3 things in it. But anyway, that's what set means. And remember, when you see the set notation and you're wondering what does that mean, it just means that the set is m over n, and here's the description of our set. Okay, here are the details. But all my sets look that way. All right. So let's turn to the next page. Now I'm on page 12. Let's consider the situation where you have a to the power n. What is a to the power n? It means you take the number a and you multiply it by itself. You keep multiplying by a. The dot means multiply, and you keep multiplying until there's n of them. Okay, n of them all being multiplied together, and that would be a to the power n. For example, a to the power 2 is a squared, is a times a, okay? And then a to the power 3 would be a times a times a. Remember that. Now the difference is a to the power 2 is not the same as 2 times a. That's an easy mistake to make. But remember, when you see the exponent, that's what this number on top is called. When you see the exponent, visualize yourself copies of this stuff, okay? Make clones of it. So you have all these clones standing in line, and they have to all multiply by themselves, multiply each other. Okay, imagine all the clones. Then, so when you have a to the n, then you imagine n clones all lined up. They all have to be multiplied. So that would be the difference. And to write it down this way is a time-saving device, so that we don't have to write out that many a's all being multiplied. And now next, let's consider the order of operation. When you have a bunch of stuff being multiplied plus, how would you do it? There is, for example, consider this problem right here. Okay, a standard problem. You have some plus, some minus, and then some multiply. Now and then even something to the power 2. Now the thing that's to the power 2, it always applies by itself. Okay, 4 is being applied. 4 is being squared here, so you need to square it. But what about the others? Now the rule for this type of thing is you have multiply and divide is this. And please memorize this. It's called first multiply and divide, then add and subtract. And I have that written down in the video description below. So that's the first rule. So once you memorize that, then everything is pretty good. Now, what about multiply and divide? Which ones should you do first? That makes no difference at all, okay? And so within multiply and divide, it doesn't matter which one you do first. But when you have both multiply and divide and addition or subtraction in the same problem, then the multiply and divide has to go first. Why is that? Well, it's just tradition, okay? That's how we've always done things. So that is a standard rule in math. Now let's to consider that, let's do this problem right here. Now we have, for example, 24 times plus 6 divided by times 2 thirds, etc. So what is that? then if you do the math in your head, okay, we have 24. The second 6 times 2 over 3 is 12 divided by 3 is 4. That's 28. And 4 squared is 16. 28 minus 16 is 12, I believe. Yep, see, that is the answer at the bottom. All right, so that is how you do things. Now, having said that, please do example 6 on page, what is that, 13 as part of your homework. Now, it's very important when you take a video course like this to do all the homework, and including the examples that's in the book. And you might wonder, but the book already told us how to do it. Why should I do it? Here's why you should do it is being that the book told you how, that makes it very convenient. Then what you do is you look at the problem, but you don't look at the answer. Then you try to do it yourself. And if you have a question or troubles or whatever, then you look a little bit of the answer and get a clue out of it. See, so basically the answer itself is like a detailed answer key. That's why it's very important to do all the examples. Now let's look at now specifically I want to mention that part C of example 6 where you see this thing here. Look at part C, okay? Now, you see those bars around 5 minus 8? That is the absolute value. That means that if absolute value means you get rid of the negative sign, okay? For example, in this case, the absolute value of 5 minus 8 is 5 minus 8 is minus 3. You take the absolute value, it becomes positive 3. You just throw the negative sign away is what the absolute value sign does. That is called the absolute, the 2 bars, okay, vertical bars are called the absolute values symbol. And what you do is you kick out the negative sign if it has any. If it doesn't have a negative sign, then you're good. If it has a negative sign, throw it away. And so that's how you would do that. And also like part D. Now look at part D carefully. Okay, now as I have told you, we need to first multiply and divide, then plus and minus, right? So how do you do part D? Well, part D, the division line is across the whole thing. So you do have to finish what is on the numerator, everything on top, and then finish everything that's on the bottom. And after you do that, then you do the division, okay? Because there's no other sensible way to do this thing. So remember that. When it comes to division line, it depends on how long it is. If it's all the way across, then you have to do everything on top and then do everything on the bottom, and then do the fraction part. So please do example 6 as part of your homework. Next, let's go to page 15, and where we have the situation we have a number multiplied by something that's being added. How would you add that? Now take a look at this, okay? Let's say we have 3 times 7. That's I have 3 here and 7 here. So that equals to 21. But what if I were to cut this up so that it becomes 3 times 2 plus 5? Okay, I have 2 here and 5 here. Now the way you do it is you take 3 and multiply by each one and add it up. As you see, 3 times 7 is equal to 3 times 2, the first chunk, and then 3 times 5, the second chunk. See, that's why it makes sense. So when you multiply this kind of thing, then you will take the number outside and then multiply it by each number on the inside. It's kind of like there are 2 groups, okay? You have a group here and a group here. The group here is like this guy will shake hands with every guy in the group, okay? The group, they don't shake hands among themselves. They only shake hands with the other group. Now this is also true when we have if 3 is in parentheses here, but I guess we are not going to talk about that right now. Actually, why not? For example, let's say 3 equals, we'll break 3 down equals to 1 plus 2, and then times 2 plus 5. Now, how would you multiply these together? Now, the same principle applies, is that each guy in this group will shake hands with each guy in this group. One time, okay, that meeting, nobody shakes hands with people in their own group. You're meeting a new group, okay, and then everybody shakes hands with the other guy. So what you do is this equal to you break it down, equal to 1 times 2 plus 5, okay, and then plus 2 times 2 plus 5. Why? Because each guy will shake hands with each person in the other group. Okay, so that is how this kind of stuff works. So knowing that, let's look at the next thing. Oh, I should also mention, what if there's a negative number here? If there's a negative number, say minus 2 plus 5, what that means is that you have, minus just means minus 1. Okay, it's the same as having minus 1, so you take minus 1 times 2. That you will be equal to minus 2 and minus 5. In other words, the minus sign will shake hands with each item inside, okay, to get to that result. So that's how you handle stuff that's being multiplied in parentheses of stuff that's being added or subtracted. Now, having said that, let's look at an example. Okay. Please do example 7 on page 16 as part of your homework. And then next, let's evaluate algebraic expressions, which that just means you need to plug something in. As an example, let's look at example 10 on page 18. All right, so let's go to page 18. Example 10, which says we have a bunch of stuff, formulas, and then you're supposed to plug in the value of x. For example, let's look at part A of example 10 on page 18. We have x plus 5, okay, for x equal to minus 5. So you will use the value minus 5 as the value for x. So you plug that right in there. It becomes minus 5 plus 5, and that will be equal to 0, see, as it says. Now that is true for other things as well. Let's look at, for example, part D, where part D you have a bunch of stuff. There's A and B and all that stuff. It doesn't matter. A is 11 and B is minus 8. So you put A as 11, and then 11 plus 11 times negative 8, and then plus negative 8, and figure out what that is. It is equal to something. Anyway, so please do that as part of your homework. Next, let's look at example 11 on page 19, where we have some cylinder, okay, and we have a cylinder. We don't really care that it's a cylinder right now because we're given how to do it, basically. The way to do it is right here. Here's the surface area that you're supposed to calculate. It doesn't matter how it got there. The point is we're given what the value of R and H is. So then you just plug it in. R equals to 6 or something, and H equal to something 9, and whatever. You plug it in, okay, and then you do you write it out and leave the answer as pi, which means you don't even have to use a calculator to do this. So please do example 11 as part of your homework. The same with example 12 and 13, which are well, sure, a nice little review for various algebraic manipulations that we have done. So for homework, and do all the examples. That is extremely important. Okay. Now, and also do the homework that I have picked out, which is the description. This is also in the video description under this video. Is on page 21, problems number 7, 13, 17, 25, 27, 37, 41, 45, 49, and 51. That is and all these, most of the homework I assign are odd number problems because the odd number problems have answers at the back of the book, and then you can check yourself to see if you got it right. That is okay. I won't be going over the homework, I don't think, because they are fairly straightforward. And if you can't get the right answer, that just means you probably, well, need to do it again, or do it on after you take a break or something until you get it right. It is extremely important that you get everything, that you know everything in this section. All right, and the homework, once in a while the book might have a mistake. So if you do the homework several times and can't get the right answer, it's possible that the book might have an error, but make sure that you double check your answer like several times and before you come up with, before you decide any such thing as the book answer is wrong, because chances are, I'm afraid, that you or I are the ones who are wrong rather than the answer at the back of the book. So please go do your homework, and that should mark the end of this section.